So the next set of functions that we are going to see are greatest integer function and fractional part function. So now let us look at what greatest integer function is. So this function is also called floor function or integer part function. Integer part function. So greatest integer function, floor function or integer part function, all these represent the same function, and f of x is equal to integer part of x. So this is the notation. So if I write a number in square brackets, that means integer part of x or greatest integer function of x or floor of x is defined in English as the greatest integer less than or equal to x. That's the definition of integer part function. So integer part of x is the greatest integer less than or equal to x. That is, for example, so if you have the number line, like this. So now what is the integer part of 2.3? If I ask you to find the integer part of 2.3. So by definition, integer part of 2.3 is nothing but the greatest integer less than or equal to 2.3. So if you take the real number line, we know that 2.3 lies somewhere here. 2.3 lies between 2 and 3. Now consider all the integers less than or equal to 2.3. So obviously get all the integers on the left side of this number, right? And out of all these integers, what is the greatest integer? The greatest integer is nothing but 2. So integer part of 2.3 is 2. And what is the integer part of 5 or 3.5? What is the integer part of 3.5? So 3.5 lies somewhere between 3 and 4. 3.5 lies somewhere here. So consider all the integers less than or equal to 3.5. Consider all the integers less than or equal to 3.5. So out of all the integers less than or equal to 3.5, which is the greatest integer? So obviously 3 is the greatest integer, right? So let us go for another example. What is the integer part of 1 itself? So if you take an exact integer here, what is the integer part of 1? So let us consider 1 on the real number line. 1 is here. So consider all the integers less than or equal to 1. That is, you have to start from 1. So 1, 0, minus 1, minus 2, minus 3, so on. If you consider all these integers, what is the greatest of that? 1. So right. So do you understand what is going on? So this is how we calculate integer part for positive numbers. So even for negative numbers, let us take some example. Integer part of minus 1.5 is equal to. So minus 1.5 lies somewhere here. So what is the greatest integer less than or equal to minus 1.5? It's nothing but minus 2, right? So minus 2. Integer part of minus 2.35 is equal to. So where does minus 2.35 lie? Somewhere here. So consider all the integers on the left side, that is less than or equal to this number. Out of all those, what is the greatest one? Minus 3. So what is the integer part of minus 1 itself? So what is the integer part of minus 1? Minus 1 lies here. So if you consider all the integers less than or equal to minus 1. So the greatest of all of them is minus 1. Right? So this is how you calculate the integer part of a specific number. So I hope you have understood what this is. So whenever you have 2 point something in the positive side, whatever you get before the point is nothing but the integer part, and integer part of integers is exactly same as the integer itself. And integer part of a non-integer is nothing but the closest integer to this number on the left side of that, on the real number line. So that will be the value of integer part. So you need to understand this. So if you have a negative number, minus 1.5, you're getting the next negative number, you're not getting -1. For the positive numbers, 2.3 integer part is 2, 3.5 integer part is 3, 5.7 integer part will be 7, integer part will be 5. But for negative numbers, you have one difference, that is -1.5 integer part is not -1, it is -2. -2.35 integer part is -3. So if you have an integer, exact integer, you get the same number as the integer part, otherwise you get something like this. So once you understand the physical meaning of integer part of x, let us see the mathematical definition. Mathematical definition of integer part of x. So integer part of x is a piecewise defined function. So integer part of x, the definition goes something like this. This is equal to 0 if 0 less than or equal to x less than 1. So if the number lies between 0 and 1, the integer part will be equal to 0. And the integer part will be 1 if 1 less than or equal to x less than 2. So if x is in between 1 and 2, the integer part will be equal to 1. Exactly when x is equal to 1, integer part starts becoming equal to 1. And it goes on till 2. And if x is in between 2 and 3, integer part will be equal to 2, and this goes on. And the integer part will be equal to -1 if -1 less than or equal to x less than 0. And -2 if -2 less than or equal to x less than -1. That is, if you take the real number line, 0, 1, 2, 3, so on, -1, -2, so on. So if x is in between 0 and 1, for all these values, 0, 0.1, 0.2, 0.3, 0.9, 0.9999, till that value, you get integer part as equal to 0. Exactly when x is equal to 1, the integer part jumps to the value 1. And this remains 1 till you go to 2. So exactly when you reach 2, the integer part jumps to 2. And it remains 2 for a unit interval. And then it jumps to 3, it jumps to 4, so on. So now, once you understand the mathematical definition, this goes on like this. So if you see the machine interpretation of this, what is the domain of this function? Domain is nothing but all real numbers, right? Because this function works for every real number. You can find integer part for all real numbers. And the range of this function is nothing but the set of integers. So the outputs that you get from this function are all integer values. You won't get non-integers out of this machine. So the domain is real numbers and the range is integers. Now let us try to look at the graph of this function. So if you try to draw the graph of this function, so how does it look like? So from the definition of integer part of x, integer part of x will be equal to 0 if 0 less than or equal to x less than 1. So if x is in between 0 and 1, the value of integer part of x will be equal to 0. That means the value of y will be equal to 0. That is exactly at 0, the integer part is 0, and this remains to be 0 till it reaches the value x is equal to 1. And exactly at x is equal to 1, it jumps to the value equal to 1, right? It becomes 1, it becomes 1 exactly at x is equal to 1. So you have a hollow dot here. That is, this value 0 works only till the left neighborhood of 1. That is up to 0.999999, so on. At exactly x is equal to 1, the integer part jumps to the value 1. And it remains 1 till x is equal to 2. So it works, integer part of x is equal to 1 works from 1 to 1.9999, so on. So exactly at x is equal to 2, so you represent this by a hollow dot. This x is equal to 1 does not work at exactly 2. At exactly 2, you go jump to 2, and this continues till x is equal to 3. At x is equal to 3, again you jump up, and then it continues. And in the negative neighborhood, that is between -1 and 0, so the graph will be equal to -1, right? You have a solid dot here, have a hollow dot here, because at 0, 0 works. When x is equal to 0, y is equal to 0. This is the point which works. Solid dot is the point which works. Hollow dot is the point which does not work. So at x, before x is equal to minus 1, before x is equal to 0, this minus 1 works. And as x goes beyond minus 1, the value will be equal to minus 2. And as x jumps to the left of minus 2, the integer part will become minus 3. And this curve goes like this. So as you can very clearly see why this function is also called step function. So if you consider something like this, the graph looks like steps. So that is why this is also called step function. And this is also called the floor function. So why is this called the floor function? So if you consider the real number line vertically, so if you have 0, 1, 2, 3, so on, minus 1, minus 2, minus 3, so on. So if you consider this like an apartment as a high-rise building, so this is 0 floor, first floor, second floor, third floor, so on. So between 0 to 1, if you have any number between 0 to 1, the functional value brings it to the floor. So between 0 and 1, all of these values have the functional value as 0. So between 1 and 2, all these values will be coming to the floor of this. Here also, any number between 2 and 3, it gives the floor value of the number. Similarly, if you have any number between 0 and minus 1, all these numbers will be taken to the floor of that particular number. So that's why this is called floor function also. So effectively, we have understood the graph of the function. You need to remember this. You need to remember the mathematical definition of the function, the physical definition of the function, the domain which is real numbers, the range which is the set of integers. So now this is a very special function. So there are a lot of properties that you need to remember for this function, because if a problem is given on integer part, you need to first simplify it, eliminate the integer part using properties of integer part, and then go forward with the question. So let us see the properties of integer part.